Welcome, friends. I hope you're as excited as I am to explore the rich and rewarding topic of in-context learning of representations. This fascinating work comes to us from researchers at Harvard University, NTT Research Inc., and the University of Michigan. Today, we're going to dive into how large language models, or LLMs, can adapt their understanding of concepts entirely based on new context, even when that context differs from what they've learned during training. The central question these researchers asked is, can a model alter its internal representations of concepts when provided with new, context-specific information? To investigate this, they designed a task called the graph tracing problem. Now, let's unpack that. In this scenario, a graph is a collection of nodes and edges. Think of nodes as concepts or items, like apple, bird, or car, and edges as the connections or relationships between them. These connections are defined by specific structures, such as a square grid or a circular ring. The model is given sequences that represent random walks through this graph. Imagine taking a stroll through a network of connected ideas, moving from one concept to another along the established connections. For instance, starting at apple, moving to bird, then to car, following the links defined in the graph. The model's task is to predict the next node in the sequence based on the pattern of connections it has observed. They used specific language models for this task, notably Llama 3.18b, which is an advanced AI model capable of processing and generating human-like text. By feeding sequences into Llama 3.18b, the researchers examined how the model's internal representations of these concepts changed. One of the key findings is quite interesting. As the model is provided with more context, that is, longer sequences of these connected concepts, it begins to reorganize how it internally represents these concepts. Instead of relying solely on the meanings learned during its original training, the model adjusts its internal structure to reflect the new relationships specified by the context. This reorganization happens suddenly once the context reaches a certain length, indicating an emergent behavior. But what happens when the concepts are already related in the model's prior knowledge? For example, consider the days of the week: Monday, Tuesday, and so on. These have inherent relationships learned during pre-training. The researchers found that while the model does incorporate the new graph structure provided in the context, it doesn't completely override its existing understanding. The new context and the pre-existing semantic relationships coexist, with the model balancing between the two. To understand why this reorganization occurs, the researchers introduced the concept of energy minimization using something called Dirichlet energy. In simple terms, Dirichlet energy measures how smoothly values change across the nodes of a graph. By minimizing this energy, the model finds the most efficient way to adjust its internal representations to align with the new context. Think of it like stretching a rubber sheet over a landscape of peaks and valleys. The rubber naturally settles into a shape that minimizes tension. Similarly, the model adjusts its internal map of concepts to fit the new information in the most efficient way possible. This process suggests that the model is performing an implicit optimization to infer new semantic relationships based on the context it receives. It's adapting its internal concept space to accommodate the new patterns, much like how we might rearrange our understanding when learning something new. An important observation from the study is that the model's performance in predicting the next node improves significantly once the context reaches a certain size. Initially, with shorter contexts, the model's accuracy is relatively low. However, as more context is provided, there's a noticeable increase in accuracy. This sudden improvement indicates a tipping point where the model effectively reorganizes its internal representations to better understand and predict the new structure. In summary, this research highlights the significant ability of large language models like Llama 3.18b to adjust their internal concept representations based entirely on new contextual information. By scaling the amount of context, models can flexibly adapt to novel situations, which could unlock new capabilities and applications. Understanding this process is vital for developing more adaptable and general artificial intelligence systems in the future. Thank you for joining me on this exploration of in-context learning of representations. Until next time, keep pondering the fascinating ways in which intelligence, artificial or otherwise, adapts and evolves.